A shocking space event. Pluto is a distant and mysterious dwarf planet, which was once a member of our solar system's planetary family. However, recent startling announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggest that this icy world is on a possible course of collision with Neptune. But how could this happen, and what would be the results of such a significant event? Are we witnessing a rare astronomical phenomenon, or is there something more to this impending cosmic collision? Join us as we explore the possibilities of a Pluto-Neptune impact. Pluto, a former planet with a peculiar orbit. Pluto, a former planet that was demoted to a dwarf planet partly due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent forecasts from eminent scientists, Pluto's trajectory is dangerously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the red flag about a possible hazardous collision between these two planets, which could pose a huge threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete one orbit, meaning that, since its discovery in 1930, it hasn't even finished one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the near-circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination. Angled at 17 degrees to the ecliptic plane, Pluto's trajectory is significantly steeper than that of the other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. The truth about Pluto and Neptune's orbits. One of the most intriguing aspects of Pluto's orbit is the point where it intersects with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out due to its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of space mechanics. The three-body problem. Solving space motion. The three-body problem in space involves determining how three celestial bodies, like Pluto, the Sun, and Neptune, move and affect each other with their gravity. It's like attempting to predict their destinations based on where they start and how they pull on each other. In Pluto's case, this problem helps scientists understand how its path, Neptune's path, and the Sun's gravity all interact in a complex way. Key orbital phenomena that prevent a collision. 1. Azimuthal libration. In the context of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from colliding. 2. Latitude libration. This refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is situated significantly above their orbital plane, providing an additional layer of protection from potential collisions. 3. VSK oscillation. Named after three scientists, Bond, Zippel, and F., who studied how celestial bodies move in space, VSK oscillation describes how three space objects, like Pluto, Neptune, and the Sun, pull on each other with gravity. This oscillation plays a crucial role in maintaining Pluto's unique yet stable orbital path. Even though Pluto's orbit may seem erratic, these phenomena ensure that it remains in a stable motion. The VSK oscillation, in particular, reveals that even if planetary paths appear chaotic, underlying patterns and gravitational interactions maintain order in the solar system. What scientists just discovered. Numerical simulations in the late 1980s revealed that, despite these stable properties, Pluto's orbit is technically chaotic. Even minor deviations in initial conditions can lead to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping chaos at bay. Recent computer simulations have helped scientists understand how the giant planets, like Neptune, Jupiter, and Saturn, affect Pluto's trajectory. Pluto and Neptune's orbital resonance. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's path steady. Jupiter's influence. Jupiter's gravity plays a significant role in keeping Pluto's orbit stable over billions of years. Saturn's minor contribution. Although not as influential as Jupiter, Saturn's gravity also provides additional stability. This means that Neptune, Jupiter, and Saturn all work together to ensure Pluto continues its journey through space without running into trouble. The importance of understanding Pluto's orbit. These orbital mechanics are essential for maintaining the predictability and order of celestial movements in the universe. Without these mechanisms, our solar system would be far more chaotic, with celestial bodies potentially colliding or being ejected from their stable paths. For Pluto, especially with concerns about a possible collision with Neptune in the future, understanding its orbit is crucial. It provides us with a clearer picture of the solar system's dynamic nature. The case of Pluto demonstrates how even seemingly unstable orbits can achieve equilibrium through complex gravitational forces. It also highlights the importance of continuous observation and study to better understand our place in the universe. Neil deGrasse Tyson's warning. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is vividly illustrated in Pluto's case. This means that even slight variations in Pluto's position or velocity can significantly alter its long-term trajectory. Using computer simulations has been invaluable for scientists in figuring out how Pluto moves in space. These simulations use tricky math to mimic how Pluto and other space bodies like Neptune pull on each other. By changing little details in the simulations, astronomers can see how even small tweaks can make a big difference in the region Pluto occupied in the late 1980s. These simulations showed that there is still a lot to learn about Pluto's path. Even though it has mechanisms like apsidal and latitude libration to keep it steady, its orbit can still be pretty wild and unpredictable. If you start off with just a small difference in Pluto's location or how fast it's moving, over many years, its path may ultimately appear very different. However, despite all of this chaos, Pluto's orbit stays stable for a super long time, like billions of years. This means Pluto's journey around the Sun has a kind of order to it, even though it seems all over the place at first. Predicting cosmic events, especially when they involve chaotic orbits like Pluto's, poses significant difficulties. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainties. While numerical simulations provide a powerful means to understand and anticipate the future paths of celestial bodies, they also highlight the limitations of our predictive capabilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or oversimplification can lead to vastly different outcomes, making precise predictions a difficult task. The chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made significant strides in understanding space, the case of Pluto reminds us that our knowledge about the universe still remains limited. Understanding the gravitational influences of giant planets on Pluto's orbit provides useful information about the broader dynamics of the solar system. It shows how the presence and position of each planet can have far-reaching effects, influencing the stability and paths taken by other bodies within the system. So, why are major astrophysicists only now raising concerns about a possible collision between Pluto and Neptune, despite all these complex forces working to prevent such an event? Neil deGrasse Tyson, a prominent astrophysicist and a pivotal figure in popularizing astronomy, offers a different perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in the reclassification of Pluto from a planet to a dwarf planet, provides insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unknown realms of space. Tyson's stance on Pluto's reclassification is rooted in our ever-expanding knowledge of the solar system. He views the reclassification not as a demotion but as a necessary adaptation to our growing understanding of the many bodies orbiting our Sun. His approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits, such as Pluto's, as a reminder of how much there is still to discover in space. The intrigue of these unknowns, especially the potential interactions between Pluto and Neptune, highlights the dynamic and unpredictable nature of our solar system. Tyson's work emphasizes that the more we uncover about space, the more questions arise, pushing us to explore further and refine our understanding of the cosmos. Michio Kaku, another renowned physicist and futurist, offers a different yet complementary viewpoint on the mysteries of space, focusing on the often unpredictable forces that shape our universe. Kaku is known for his ability to connect disparate scientific ideas with visions of the future, making him a significant voice in discussions about celestial mechanics and their broader applications for humanity. Kaku's views on Pluto and its orbit emphasize the need for continuous observation and advanced modeling to anticipate and understand potential cosmic events. He sees the interactions between celestial bodies as a crucial area of study, not just for academic curiosity but for practical implications. The potential collision between Pluto and Neptune, for instance, is not just a theoretical scenario but a reminder of the dynamic and often chaotic nature of space. Future space predictions. There is a general scientific consensus that, for the foreseeable future, the orbits of Pluto and Neptune remain stable due to their average motion, resonance, and various gravitational influences acting on them. Therefore, a direct collision between Pluto and Neptune is highly unlikely. However, the complexities and potential perturbations in orbital dynamics mean that astronomers must continue to monitor and study these celestial bodies to better understand their long-term behaviors and any potential risks they might pose. While the scenario of a Pluto-Neptune collision is largely speculative and considered unlikely with our current understanding, it highlights the importance of continuous research and observation in astronomy. Advances in technology, including improved telescopes and computer simulations, will help astronomers refine their models and predictions, ensuring that we stay informed about the dynamic and ever-changing nature of our solar system. Tyson's perspective on Pluto's reclassification and Kaku's emphasis on the unpredictability of celestial mechanics both underscore the need for continuous exploration and a flexible comprehension of our universe. The potential collision scenario, while unlikely, highlights the dynamic and complex interactions within our solar system. Ultimately, it reminds us of the vast, still uncharted territories in our understanding of space. The role of technology in refining our understanding. As we continue to monitor Pluto and Neptune's orbits, one crucial aspect that has come to light is the changing role of technology in advancing our understanding of these distant worlds. The use of advanced telescopes, including space-based observatories like Hubble, has significantly enhanced our ability to track these objects with remarkable precision. With the aid of such technologies, astronomers can observe Pluto and Neptune in unprecedented detail, gaining insight into subtle variations in their trajectories that were previously undetectable. Moreover, the development of more sophisticated computer simulations has been vital in modeling potential future interactions between celestial bodies. These models, which incorporate millions of variables, allow scientists to predict the possible consequences of gravitational interactions that could affect Pluto's orbit. Now that simulations are carried out with greater precision, the previously considered chaotic nature of Pluto's orbit may become more predictable over time, providing greater certainty in forecasting future scenarios. The discovery and monitoring of other distant objects within our solar system, such as trans-Neptunian objects and other dwarf planets, have also contributed to refining our understanding of the forces at play in the outer solar system. These objects often share similar orbital characteristics with Pluto, and by studying them, scientists can gather valuable data that further informs predictions regarding the stability of Pluto's orbit. While the possibility of a direct collision between Pluto and Neptune remains unlikely in the foreseeable future, it serves as a reminder of the dynamic and sometimes unpredictable nature of our solar system.